Okay, welcome to this part. In this part, we will learn the mathematics behind factorial design, and we will use the regression equation to fit our data. Previous part, we set up the experimental design, we defined the variables, we chose the levels, and we built the table with the 9 combinations. Now we have imagine we've run all the experiments, the 9 experiments. So we've made all the 9 formulations and we measured the hardness of each one. So basically we have the data. The equation is, we're going to use, like I said, here is going to be a regression equation. And the question we have here is how do we turn this data into something useful? So how do we create a mathematical model that lets us predict a hardness for any combination of binder and force. That means even if the combination we didn't actually test. And that is the beauty of this fitting or modeling. So that's what the regression analysis does. So it will find the equation that best fits our data. So this is the journey we are taking. Now the good news, raw experimental that data, you're not going to do this manually. Analysis. So all these and it comes can be done through a software prediction equation. And obviously here, this equation lets you estimate the response for any combination. So of x1 and x2 within your test will help you with the interpretation of the results. That will allow you often predict commonly use any combinations software even Excel, if you didn't directly test them. And if you are good with coding, you can use R or Python. There are other software design expert or JMP. I use Python quite a bit, so I highly recommend it as well. But for this linear regression or regression kind of analysis, then Excel should be sufficient. And we will demonstrate with the Excel tool and Excel like spreadsheet with the data, and that should show the coefficients, and it will generate some contour plots and helpful evaluation of the model fit. So here are some steps that you can follow to complete full analysis. So on the what you can do, you can input your data, enter your variable names and input, define your low, medium and high levels, and enter all 9 measured responses. Predicted values appear automatically once you have entered your data. So the tool uses your actual values, not coded, so enter what you actually have measured. The equation, which is going to describe the output, is shown here. So this is calculated using a software or Excel sheet. I'll give an example in the description to this video. So you'll have those values A0, A1, A2 or A3. Here perhaps some references they put them as beta 1, beta 0, beta 1, 2, 3 and so on, beta 2 and so on. And the idea is that the beta 0 or the A0 that represents the intercept value, or sometimes you call it the starting point or the intercept. You are measuring two factors, x1 and x2, and the strength of each one you can represent it by the value next to it. So in the image here is beta 1 or A1 here. Basically that means the strength of that factor. So if it's beta 1 means the effect of x1. Beta 2 or A2 is the effect of x2. And you can have a final term which is the represents the interaction of both of them, which is the A3 or beta 3. That basically means the interaction between x1 and x2. So it could be a3 or beta 3 or a12 or beta 12. That means the same thing. The standard errors, they will be shown, and also you will have the full equation displayed. It's very important you understand the format of this equation. To evaluate the model fit, we use R squared as the primary metric. So the predicted versus measured plot should show points clustered tightly around the diagonal line. Points that are far from the diagonal line are poorly predicted, and possibly they are outliers. Basically, there's probably something gone wrong, and they are not really within the line, or could be the model did not really fit or it failed. Random scatter around the diagonal is actually what we want. It just indicates an systematic error, and it means that you have good predictions and your model is doing well. So to make sure we have a good representation of the data, we will use a contour plot. The contour plot transforms your equation from an abstract formula into something you can visualize, so a visual map. So you need to set your axis ranges to match your experimental range. This is really important, because if you extrapolate beyond that, then it could be risky. Your model may not really fit. So just remember that. The contour lines connect points of equal response, and you can see that through the lines which divide different regions. And the color here, color code, represent response magnitude. So you can immediately see where the response is maximized, minimized, and how steeply it changes across the different range of your data. Let's work through an example with the cream formulation. So our independent variables are x1, which is the surfactant amount in grams, with levels 3, 5, and 7 grams, and x2, which is the amount of liquid paraffin, also in grams, with levels 4, 6, and 8 grams. And the response is the viscosity in Pascal seconds. The resulting equation is y equals minus 3.38 minus 0.62 x1 plus 2.29 x2 plus 1.2 x1 x2. And then if we look through this equation, if you recall from we mentioned about the different factors, so all these coefficients. Okay, so A0 of minus 3.38 is the baseline at the center point. A1 of minus 0.62 tells you that the surfactant slightly decreases viscosity. Just note the minus sign. So minus, it did affect the negatively, so it reduced the viscosity slightly, not much. A2 in this case of plus 2.29 shows paraffin. Look at the value 2.29. It shows like the paraffin has increased the viscosity. Okay, so this is a bigger effect compared 2.29 compared to 0.62. A3 of plus 1.2 indicates a positive interaction, and we said this coefficient indicates interaction between the variables, the independent variables x1 and x2. So, which means those two factors, they work synergistically together. Let's step back and understand what regression actually does. So, regression is a statistical method that finds the best fit equation for your data. So, imagine you have 9 data points scattered in space. There are definitely many possible equations that could be drawn through them. So regression finds the one equation that fits best. And I suggest that you refer to the data fitting series if you would like to understand what it means by data fitting. So how does it define best? It will minimize the differences between predicted values and measured values. The predicted values are what the equation calculates, and the measured values are what you actually test in the lab. So a regression finds the coefficient that make these differences as small as possible. Once you have the equation, you can make predictions. So you can ask what would happen at this combination. So this equation gives you an estimate based on the patterns in your data. So this is the beauty of regression, is finding patterns in data and using them to make predictions. So we've seen this equation before, but this is just a reminder again. The y is the predicted response. We call that the dependent variable, and we have, in the case, if you recall from when we were measuring tablets, we said this is the hardness of tablets. An example is hardness of tablets. We have a0 plus a1 multiplied by x1 plus a2 multiplied by x2 plus a3 multiplied by x1, x2. And we said a0 is the baseline value, all right, or the intercept at the center point. So you could imagine it's the starting point. Where do you start your output? The a1 refers to the strength of x1. A2 refers to the strength, because if you look at the example on the cream, that could either increase it or decrease it. And A3 refers to the interaction. So basically, do they work together? Do they magnify each other? So that is the interaction coefficient. Say, for example, you've done your tablet hardness experiments and you ended up with this equation. So you'll see y equals 85 plus 12x1 plus 19x2 plus 4x1 x2. And the a0 here refers to the center point or the starting point of your formulation. And then anything which deviates from that value is basically the impact of different variables. So when you have a1, that means it's a positive increase, and that basically means more of the binder, because it's x1 is the refers to the binder amount that will increase the hardness. And basically a positive increase in or increasing binder amount, that increased the hardness of the tablet, and you would expect that. Look at the number 19. You will find that more of force you applied, that also increase hardness, and you will find that of course 19 is bigger than 12, means the effect is bigger when you increase the force. And then finally you look at the interactions between them, and this is 4 plus 4. That means there is a positive interaction. So basically they work together. So this 1 plus 1 equals 3. Basically there is an augmented effect if you think about it. So and that's again, that is expected. If you increase one of them, that will increase, and if you increase the other one will increase, and both of them together they lead to higher hardness of the tablet.